Good morning, everyone, and thank you for joining the LSI last time webinar on G.Re.T.A system, electrical resistivity tomography for tailings and airtimes monitoring. My name is Federico Orlando. I work in the LSI last time international sales department, and I will be your host today. Let me start by saying that we are truly thrilled by the success of this event. We have received over 200 registrations from 31 different countries, proving that there is a great interest in this topic. Before handing over to Greta Tresoldi, who is the main speaker of this event, I'd like to share a few housekeeping notes. So at the end of Greta presentation, we will have a question and answer session. And given the high number of attendances, I kindly ask you to submit your question anytime using the chat function. I will do my best to address as many as possible. If we don't manage to answer your question live, don't worry, we will get back to you by email. And last but not least, this webinar is being recorded and it will be available later on the LSI Lastem YouTube channel. So that's all from my side for now. I'm delighted to invite Greta Tresoldi, Product and Marketing Manager at LSI Lastem, to take the stage and guide us through the fascinating world of the ERT for tailings and air dams monitoring. So thank you, Greta.
Good morning and good afternoon to all the participants that are logged on from all over the world. Thank you, Federico, for the presentation. I'm Greta Tresoldi, Product and Marketing Manager from LSI Lastem, and today we will delve into the topic of electrical resistivity tomography applied for tailings and dirt dam monitoring. Then we will focus on the G.Re.T.A system, georesistivimeter for time-lapse analysis, and we will see some interesting case studies. But we need to start from the basis. So ERT method is part of geophysical measurements. So just a brief introduction on the all geophysical measurements. Some of the key points of this kind of measurements: they are all non-invasive measurements, so you will obtain some parameter of the underground without excavating, without extracting samples. All these methods are based on physical properties of the soil, and they are indirect measurements. Thanks to that, you can obtain soil characteristics. The geophysical world has different methodologies, for example, seismic, electromagnetic, gravimetric, and electrical methods. All these methods are divided into passive, where you detect the variation within the natural fields associated with the Earth without transmitting any signal inside the ground. And then we have the active ones. So they are based on artificially generated signals that are transmitted into the ground. The ground acts like a filter and then modifies the received signal in ways that they are characteristic of the material through which they travel. So speaking about ERT measurements, we are in the field of electrical methods, and these measurements are active. So we are injecting an electrical field inside the ground, then we are measuring the voltage, and we are obtaining some parameters. So focusing on this method, so electrical resistivity tomography, as previously said, they are indirect, they are geophysical measurements based on the propagation of the electrical field due to soil properties. So the electrical field is modified thanks to the different properties of the monitoring area. Thanks to this method, you can obtain a bidimensional reconstruction of the soil electrical properties. Mainly, you are obtaining the resistivity of the soil. And why resistivity is so important to us? Because the resistivity changes based on soil composition, water content, presence of voids, and fluid resistivity. These kind of methods have been used since the mid-90s, but so far have been used with portable instruments. So how does it work, the measurement? You need the system, a georesistivimeter, then you need electrodes in contact with the soil to inject the electrical field, and then you need the cables to connect every part of this hardware. So you inject an electrical current and measure the voltage. We have many electrodes, so we can perform many measurements because, as you can see here, the okay, as you can see here, we can obtain different measurements in a shape of a section using different electrodes. We use, for example, the Venner array. So we use two electrodes to inject the current, C1 and C2. Then we use inside other two electrodes to measure the voltage, P1 and P2. And we obtain one value. Using different quadruples, increasing, for example, the spacing between these electrodes, we can reach the deeper part of the section. Obviously, since we are increasing the distance between the electrodes, we have less data in the deeper part. This is a geometrical principle, and all the E.R.T. measurements are done with this principle. So you obtain the raw data thanks to the second law of Ohm. Then you need to process the data. So you need the tomographic inversion. It's an iterative procedure that provides like a picture of the underground in terms of resistivity. So which are the main pros of E.R.T. measurements? First of all, they are a good proxy of water content. So water influences the resistivity of the soil, and in a given soil is strictly related to the variation of water content. Then you will obtain a bidimensional data, not only one point. It's like a picture, or in monitoring is like a movie of the underground. And you can investigate large areas. In this case, you can see here that we have a profile of 141 meters and the depth of 22.5 meters. So big areas, not only one point. And you don't need to core to obtain these values. But now we can focus on the G.R.E.T.A system. E.R.T. measurements are applied for monitoring, and all the system is totally automatic. So which are the pros of automatic E.R.T. monitoring? First of all, you have a fixed installation, so you install the system only one time with a standardized procedure, and you don't need to go on site to perform the measurement. Then we are performing a monitoring. So the most important aspect is the evolution of what we are looking at. So the evolution in a given soil are mainly related to water infiltration, cavity formation. All the part related to the processes, so the processing, the inversion, is totally automatic and on the cloud platform. And also, if you want to repeat the measurements, you can configure the system from remote. So what you can do with automatic E.R.T. monitoring? You can follow over time the evolution of many underground processes, addressing the problem before it's too late. Because if you see the result of the process, so for example, a displacement, it's too late. Okay, so step forward, how automatic E.R.T. can be applied for TSF monitoring or earth dam monitoring or LV monitoring also. Geoelectrical monitoring offers valuable insights for different water-related processes. For example, can give a hand in identifying concentrated seepages, detecting under seepages, analyzing the saturation over time, and not only in fully saturated soil, because the electrical current can pass also in partially or unsaturated soil, so you can have some information on the percentage of water content. And also you can follow this saturation over time or assess specific processes such as the dewatering processes in a dam or the evolution of groundwater level. Obviously, all these processes are strictly related to the assessment of the stability over time of the dam. So, what is this georesistivity meter for time-lapse analysis? It is an off-the-shelf, autonomous, cloud-based, fully automated georesistivity meter that we have specifically designed for the long-term and permanent E.R.T. monitoring. It is composed of different parts. So you have an hardware part, you have the cloud software because the system is connected through the web to a cloud, and then you have the visualization platform. Other important features are related to the remote programming of the system, the possibility of retrieve real-time data, the automatic data inversion, and those, obviously, as we have already said, the cloud-based solution. This cloud-based software can be also integrated or in other third-party platforms, or can have inside data coming from a meter station, piezometer, directly connected to the system, or also through APIs. So what are the advantages of this technology? First of all, the estimation of water content. Resistivity and water content are inversely related. So the higher the resistivity, the lower the water content, and vice versa. So since our system is installed in a given soil, the resistivity changes are mainly related to water content variation. And in homogeneous soils, or soils composed by mainly the same material, like most of TSF, resistivity is an excellent proxy of the water content. So the G.R.E.T.A system can assess changes in water content and can help to proactively predict the creation of seepages, infiltration, anomalies that may become a risk to the structural integrity of tailing dams. Here we have this scheme that can explain a little bit better this relation. So this is a tomographic session of a site that we have in South Africa. Here we can easily identify this shallow layer with this red color. So if we look at the scale of the resistivity, it means that we have high resistivity. It means lower water content, so the resistivity is inversely related to water content. In this bottom part, we have these blue values, really, really low resistivity. It means that here we have higher water content. And here we can easily identify the phreatic surface that is the boundary between these two areas. Other advantages, for sure, the fact that you can use the system as an early warning system, since the G.R.E.T.A system is totally autonomous, can follow the processes over time, but the user can also set some alert thresholds. So can receive an email if something is changing. So for example, variation in water content, onset of seepages, formation of fractures. So it's really, really useful. Other advantages are related to the comprehensive information that you can retrieve from this system. So for example, the extensive coverage. So unlike other sensors like piezometer, which provide only punctual localized data, the G.R.E.T.A system delivers a big image, a big section of the underground. Usually the profile spans hundreds of meters in length and tens of meters in depth. So you have a full picture of the underground in the monitoring site. Another important point is the enhanced water content monitoring. While piezometers, for example, only indicate the pressure and the groundwater levels, the G.R.E.T.A system can estimate the soil moisture percentage even in unsaturated condition. So all these topics are related to the proactive risk detection. Unlike other monitoring system, like the one that measure displacement, G.R.E.T.A can predict the result, so can spot, for example, the seepage and not the result that is the displacement. And after all, also the fact that the system is really easy to install and the installation is really fast. You don't need to drill, and so it's easy to set up with minimal effort. Here you can see some picture and scheme of the hardware part. The system is composed of an EP66 box, and inside the box you have different modules. This is also useful for maintenance, and you have also a battery that is charged by a solar panel if it's present. If not, you can directly plug the system to the electric grid. And then we have a modem router for the communication. Then the hardware part is composed also of 2 cables with 48 electrodes. So the number is fixed. What can be changed is the distance between the electrodes that can influence the length of the profile and the depth of investigation. We can have 2 types of installation and 2 types of electrodes. These are the electrodes that inject the current. If you want a long-term installation, you need to use these plate electrodes. Are stainless steel high-grade plate electrodes. They are buried with the cable in a shallow trench, and then they are covered. While if you want to perform a medium term, because we are always speaking about monitoring, so not only one measurement, but medium term, month, for example, monitoring, you can use pickets, stainless steel rod electrodes. Obviously, the problem is that these rod electrodes must be hammered inside the soil and the cable remains on the surface. So can be damaged, for example, from animals, people, machinery. So it's quite risky. Okay, passing to the second part of the system, we have this cloud platform, and the system is permanently connected to this cloud-based software that allows visualization, data processing, and also configuration. In the home page, you can geolocalize your system on Google Maps, and then you can also upload pictures, files, documents, and metadata. Obviously, you can visualize the data, both the inverted data and the raw data. You can change some tools for the graph, the scale, and you can select the measurement inside the calendar. You can perform manual comparison between different sessions. For example, here we have 2 different measurements in 2 different days, before and after the rain. And we can see here, this is the percentage variation in resistivity. For example, in the surface, we can appreciate this negative variation. It means that rainfall water is infiltrating inside the soil and the water content is increasing. It is possible also to download the data manually, one by one or massively, or set up an automatic export to other third-party software through APIs. The system allows also quick analysis directly on the visualization page. You can select the area of interest and retrieve minimum, maximum, and average value. But there is a more complex analysis part with many features. You can select, for example, an area in the section and obtain the minimum, maximum, and average value a long time. So it's time lapse, and you can correlate these values with rainfall, like in this case, or with piezometric data. The platform is not only for data visualization and analysis, but also for configuration. So you don't need to go on site to configure, for example, the frequency of the measurement. You can send everything to the device. Is it possible to set alarms based on different logics? So, for example, thresholds on percentage change or thresholds on absolute value. And it's also possible to select different parts in the section with different logics. As I've previously said, it is possible to integrate also additional data. So, for example, weather data. In this case, we have rainfall data for APIs and also piezometric data. In this case, you can also visualize the position of the water table directly on the map of resistivity. Now, the last part on the cloud platform, you can also calibrate the system. So if you take some core samples at different depths at site near the system, you can measure directly the water content in the lab, and then you can insert inside the platform a relationship between resistivity and water content so that you can convert your resistivity map in a water content map. Now we are halfway to the presentation. We are in the part of case studies. I think they are really inspiring, and here we have some of our installation. The system has been commercialized in 2020. We had many experience also in other fields of application like river levees, landslides. Here I report our installation in tailings dams. So we have a copper case studies in a copper mine in Chile, a gold mine in South Africa, a bauxite mine in Australia, platinum mine in South Africa, and iron mine in Brazil. The first one is the tailings dam monitoring in a gold mine in South Africa, performed in 2022. Since it's the first case studies, I want to focus a little bit more on the step for the installation that is really standard and easy. The step 0 in the office is the configuration of the modem router with the local SIM card. Then we have the step 1 is the excavation of the trench and the plinth installation. In this case, you see a big machinery, and the trench also itself is quite big, but you will see that the cables and electrodes are really small, and so the trench could have been more shallow, for example, and also less wide. The step 2 is related to the box and solar panel mounting. You can see from the picture that in this case, the system was installed on the crest of a dam, and the objective was the analysis of possible infiltration of rainwater and also seepages from the pond. Here, the step 3 is the cables laid down and the electrodes assembly. Here you can appreciate how big is the trench compared to the cables and electrodes. These are the electrodes, and in this case, the distance between the electrodes is of 3 meters. So we have a profile of 141 meters and the maximum investigation depth of 22.5 meters. Step 4 is really crucial, really important, is the electrode coverage. Since the electrodes must stay in good contact with the surrounding soil, you need to mix really well the soil with bentonite and water to guarantee this coupling. And to test the functioning of the electrodes, you need to perform the contact resistance test. Here we see an example. You have the number of the electrodes and the value of resistance. What is contact resistance? Since we are speaking about injecting a current inside the soil, we need to test the circuit. So we inject current in one electrode, then we measure the voltage in all the other electrodes in parallel, and we see if the circuit is working well. So if this value of resistance is low, mainly below 1000, it means that the electrodes are working well. So after all, we can close the trench, and then once turned on, the system automatically sends the measurement to the cloud platform. Okay, in this case, we have a quite homogeneous soil. If you look at the resistivity scale, the values ranges between 15 and 35 mol per meter, so values are quite similar. And we notice that the surface is a little bit wetter, so we have resistivity values that are lower. And at site, we don't have a piezometer, but we know that the groundwater level is almost at 15-meter depth. So it's almost here where we see these values of 25 ohm per meter. Here we report, as an example, a comparison between two measurements, one before the rain and one after the rain. We can appreciate the negative variation, so the blue part, that is the infiltration of the rainwater up to 10 meters of depth, so you can spot these homogeneities in your dam. Another case studies is the tailings dam monitoring of a bauxite mine in Australia. The steps are always the same to perform the installation. You can see that the trench now is really smaller. In this case, we are in a capped, in a closed facility. And the objective of the user was to assess the dewatering of a downstream embankment of the dam. So here you can see the cables laid down, the electrodes assembly, the electrodes coverage, always the same steps, really easy to do. And here we can see the result, the inverted resistivity that we have already seen in the previous part. So here, all this blue part is with a really low values of resistivity, around 1, 2, 3 ohm per meter. So this part is fully saturated. You can also see that the integration of the piezometer with the phreatic level that is in good correspondence with the resistivity. So here you have this point indicating the groundwater level, but here you have all this long picture. There is a stratification. On the surface we have higher values, meaning that the soil is quite dry, and in the middle part we have a partially saturated soil. We could also spot a part with a lower resistivity in shallow depth, so higher water content. Here you can see the 1-year time-lapse analysis from the installation of the first 4 meter of soil. So thanks to the cloud, we selected the shallow part, so first 4 meter, and we could retrieve the average, minimum and maximum. Here we have the average value over time, and we plotted them with rainfall. So we can see that during the dry period, mid-July, beginning of October, the resistivity was increasing because there is no rain, so the soil was drier. Then we have a stable period, and then during the wet period, we can see this drop-off of resistivity. But after the rain, the resistivity increases a lot. So after 1 year, we could assess the increasing of resistivity of 25%, meaning that the soil is getting drier, so assessing the dewatering process. Here another case study is a platinum mine in South Africa. In this case, the system was installed on a bench of tailing dams, and also in this case, the objective was analyzing the seepage and also the result during a really dry period, so analyzing the impact of climate change in the site. Here you can see always the same steps, really standard. The contact resistance here a little bit higher, but good. Another diagnostic tool that you can use in the platform is the standard deviation analysis. So this is the E.R.T. section, and every data point is acquired not only one time, is acquired multiple times in the same measurement session, and then some statistics are retrieved based on, for example, the average value and the standard deviation. So if your standard deviation is low, it means that your data are of good quality. In this site, we have really low standard deviation values below 0.2. Usually, a good data has standard deviation less than 2-3%. So in this case, the measurements were really stable. And also we can see the RMS error. It's the error of the inversion iterative procedure. So how far is the result from the model? So 3%, 2.5% is really good for this site. This is another kind of visualization of the same inverted data. So we selected the contour plot option, so we can appreciate the vertical stratification in the site. So we can see the surface with high values of resistivity, while the bottom part has really low values. In the middle, we have this vertical stratification, meaning that this part of soil is partially saturated. We could also spot a potentially critical zone with higher water content in the central part. In the site, we don't have a piezometer, but it's quite easy to understand that these really low values of resistivity are related to saturation. Here we can do some resistivity comparison. As I told you, the period between installation 2023 and now was of extreme drought. So comparing the data during installation and the data of the starting of the year, we can see also visually that resistivity has increased a lot, and the percentage difference show an increase of 400%. So the soil was really dry, and also the groundwater level decreased. The last 2 months, January and February, were really wet. In opposite, the wet season was with a lot of rain. And so we can compare the starting of the year before the rain and the end of February. We can see that the situation is really different, and we can spot the percentage difference with a negative variation of minus 80%. So water infiltration from the rain reaching even 15-meter depth. Overall, analyzing the first data, August 2023, and the last data, February 2025, we can see that the surface is with lower resistivity value. So since it's raining, the water content in the shallow part is higher, but in the deeper part, the soil is again drier compared to the starting of the monitoring. Thanks to the platform, we can perform this kind of analysis, time-lapse, and obtain this graph. We selected the shallow part, and we could retrieve average, maximum, and minimum values of resistivity a long time. From the starting of the year, we could assess the decreasing of resistivity thanks to the rain. And also in the medium part, so rainfall is infiltrating also in the partially saturated part. The last case studies in iron mine in Brazil, the steps are always the same. The objective in this case was following over time a known seepage, installing the system downstream the dam. And we can see that here we can plot the apparent resistivity, so the raw data before the inversion. In this case, we can see that the values of resistivity are higher compared to the other side that we have. It's an iron deposit, but we can spot this low resistivity value at surface every 10 meters. Then we discovered that was an artificial network, probably of metal pipes, but the rest of the section you will see in the next slide underline really well the seepage. Speaking about the standard deviation of the measurements, we have good data at standard deviation below 2%. Here, the result of the inverted resistivity, as I told you, we could easily spot the infiltration and this critical area in the middle of the profile in the deeper part. Looking at the scale, we have really high values of resistivity, but here we have really low values. So it's a saturated part, it's the seepage that was already known, and we can use different visualizations or the heat map or the contour plot to underline better some abrupt changes. Obviously, this area is a critical area that needs to be monitored. Okay, we are at the conclusions. We have seen that geoelectrical measurements in general provide useful information for tailings and air dams, but also for levees, also for water dams, for all these processes that are related to water. So we are speaking about seepage, saturation, but also the watering processes, the assessment of the groundwater level. That is because resistivity is strictly related to water content, so there is this bond between the two variables. And then we analyze the geoelectrical automatic monitoring, so it's a step forward, and the possibility of following over time this process is really key. because so far these kind of measurements have been always portable with single measurements, but now we are not taking a picture of the underground, we are taking a movie. So we can follow the evolution in real time. We saw how the G.R.E.T.A system can be really effective. It's an off-the-shelf solution, and it's obviously a strong opportunity for the mining industry to improve the TSF monitoring strategy over time as requested by GISTM. So what we want to do, what we want to say about this system is geoelectrical monitoring made easy. So really easy to use for many different kind of users. Okay, now I want to go for a short cloud platform live demo. So we will go at the website and see the different parts. And after that, we will have the Q&A session. Okay, this is the home page of the cloud platform. Here the user can spot its own system, can geolocalize the system on the map, and clicking on this green dot that is the position of the system, it is redirected to the site of installation. So this black dot is the position of the station, while the yellow line is the position of the cable. In this case, it's the site in Australia, the kept facility, and you can see that the system is positioned on the embankment downstream. Here you can see some information about the system, some pictures, some files that can be uploaded, and the name of the system. Clicking directly on the yellow line, that is the cables, you are redirected directly to the data. So here you can see this is the inverted data at site in real time. So here we have all the different measurements. So here you have this section. You can see and check the resistivity values. You can have some information about the date, about the configuration, some parameter of the inversion. Here you have the name of the site. If you have multiple stations, you will see here. And you can change some, for example, the color scale, some parameter of the graph. What you can do is also you can select an area and you will have the minimum, maximum, and average value of this specific area. As I said, it is possible to download the data in different formats, and also you can see the raw data, so the apparent resistivity data. It's the raw data acquired by the system before the inversion. And you can also look at the standard deviation of the measurements, so really good at site. And in this particular site, we have also additional data. So you can look at the additional data here. For example, we have rainfall, it's raining at site, and we have the piezometer. So here you have the numerical values of the depth of the water table, and here you have the visualization on the map. Then what you can do is you can compare different measurements from different days. So we can select two different days, 9 and 10 of March. And here we have the difference. You see a lot of colors, but if you check the values, they are really low values of variation. So 3%, 2%, below 5% is below the noise of the site. So the situation between 9 and 10 is stable. Another important part is the contact survey part. It's a diagnostic tool to check the functionality of the electrodes. So here you can see the number of the electrodes from 0 to 47, and here the resistance value associated to each electrode. So you can control and you can see if they are working well, if these values are below 1000. So here the values are really low. Then we have a configuration part. You select your system, and then you can change some information. You can modify the frequency of the data. For example, the contact test, usually we do them once per week, and the E.R.T. measurements, we do them once per day. And then you can send to the device all these modifications. The important part for sure is the analysis tool. You can select a site, a station, a period of time. So for example, starting from the starting of the year, we can go until the end of February. We can retrieve all the section. Here we have all the data. We select them and we can massively download them, or we can analyze, for example, the standard deviation on time, or, and a really interesting part, make the time-lapse analysis. So we select, for example, the shallow part since it's partially saturated, and we can send a request, test shallow part. We create a request. Here we have all our analysis requests, also for example, this one that I did yesterday. I have the graph. It's a responsive graph. We can see our data, the average, minimum, and maximum value. We can download the graph, or we can also download the spreadsheet. So you can easily open it with Excel, for example. And here I have all my analysis. This is the last one. It's pending, but probably now is completed. So it's really fast. And here we have this graph that I showed you in the presentation about the decreasing with rainfall in the first 2 months of 2025. The configuration of alerts is something interesting. We can create a new configuration, alert seepage. I can select the grade, so warning, for example. Here I put the name of the email of the person that will receive the communication. Then I can add different evaluation areas. So I can select, for example, the surface and name this area surface. Then I can select the variation. So alerts me if something changes, so if resistivity changes of 50%, not only 1 point, but at least 3 points, and compare the data of today with the data of yesterday. And also no matters if one data is missing. And then I can save, or I can add another area. For example, I can call it saturated area. And now I can select, for example, these alerts based on absolute value. So alerts me if the resistivity in this part goes below. I can check here the value, I don't know, 30 ohm per meter. That is it's the saturation in this site. I can select, I don't know, this area. And not only 1 point, but at least 3 points. So I can really configure the alerts part and receive different mails for different parts of the section, and also for example, different seasons. So one alerts for the summer season, one for the winter season. Here I can see all my archive of past resistivity alerts. Then I have a diagnostic part. I have a company part with all the information about my company. And also I have an administration part. I can create new user, change the password, activate the licenses. So it's really, really handy and really easy to use, user-friendly, and can give a hand in assessing the safety of the facility. Okay, now we I can pass the ball to Federico for the Q&A part. Thank you very much.
Okay, thank you, Greta. Lots of interesting information indeed. So, as said before, it's now question and answer time. So, first of all, I would kindly ask to Andrea Certo, CEO of LSI Lastem, to join us with the camera on to answer some of the questions. So, we received actually a lot of questions showing that the interest in this topic is really high. Unfortunately, I won't be able to read all of them, but I've tried to summarize most of them, and I can see that several questions are somehow going around the topic of the business model. So I guess I see what is the business model of LSI Lastem for the G.Re.T.A system? Do you sell or do you rent the equipment? How does the software license work? And do you provide data analysis and consultancy services? So I guess that most fitted person to answer this question is Andrea Certo, CEO of LSI Lastem. So I let him reply. Please, Andrea.
Thank you, Federico, and good morning, everybody. In general, let me answer. In every country, we try to work with local distributors that not only sell the equipment, but also provide the installation and the maintenance work after it. In the price of the equipment, the first year of the software license fee is included. And from the second year onward, the customer somehow pays an annual subscription to use the cloud platform. And in that price, it is also included all the software upgrades and improvements, so adding new features and new functionalities that happen all the time. Talking about renting, some local distributors, like in Brazil, for instance, as an alternative to the sale of the equipment, they offer a kind of monthly, longer-term full rental scheme. But this is, I would say, very much up to the local distributor to decide whether to offer such a rental scheme or not. As far as data interpretation or consultancy services, let me clarify that we, as LSI Lastem, are technology provider only. We are not at all involved in site-specific data analysis or interpretation. We leave this to the final customer or the engineer of record or other specialized consultants that have certainly a comprehensive view about what's going on at site. I think I have probably covered the most of the questions.
Yes, thank you, Andrea. I have another question from the audience, and probably Greta, you are the best person to answer to this one. Someone asked, do you always need the calibration of the system through core samples of the soil to be able to correlate resistivity with water content? So please, Greta.
Thank you very much for the question. The answer is no. You don't need every time the calibration of the system thanks to core samples. Also because if the resistivity section is deep enough to underline the water table and the saturated part, is it quite easy, as you have already seen, to understand which is the resistivity value of the saturated part. And moreover, if you have a piezometer on site, it's quite easy to correlate these two variables. Obviously, if you want to convert the resistivity section into a water content percentage section, so yes, you need to do a core sample near the system, near the profile. Then you need to extract core samples at different depths, bring them to the laboratory and measure directly the water content. If you have these values of water content and then you have the values of resistivity, you can insert this calibration curve inside the platform, and automatically you will have also not only the resistivity section, but also the water content section.
Okay, perfect. Thank you, Greta. I think that we have still time for one last question. From the chat, I see what would be the maximum depth Greta system can monitor? So I think, Greta, you can answer this one as well.
Okay, thank you again for the question. As I said, the maximum investigation depth of the system is related to the distance between the electrodes. Since the number of electrodes of the G.Re.T.A system is fixed, is 48, what you can change is the distance between the electrodes. So usually the standard system has a distance between the electrodes of 3 meters, with the maximum investigation depth of 22.5 meters. In some cases, in some soils that are not so resistive and not so conductive, we can also provide cables with 5 meters between the electrodes. Obviously, it's better to know before some characteristics of the soil, for example, the resistivity, if you have previously done measurements, for example. And the maximum depth in that case would be 40 meters.
Okay, amazing. So, all right, ladies and gentlemen, we have now reached the end of our webinar. As I mentioned earlier, if your question was not answered during the live session, don't worry, we will follow up with you by email. And additionally, another information, a PDF copy of today's slides will be shared with all the participants soon, shortly, and you will also find inside the details of G.Re.T.A Tresoldi and Andrea Certo, should you wish to reach out for further clarification, or discuss your project requirement, or simply request a quotation. So I would also like to take the opportunity to inform you that LSI Lastem will be showcasing the G.Re.T.A system at 4 major events worldwide in the coming months. So in Chengdu, China, from May 16 to May 23, at the ITCOL International Conference. We will be in Brisbane, Australia from July 29 to 30 at the 2025 Mine Waste and Tailing Conference. We will be in Santiago, Chile in September 3 to 5 at the Tailings 2025 conference. And lastly, we will be in Banff, Canada, November 2 to 5 at the Tailings and Mine Waste 2025 conference. So on behalf of LSI Lastem, I would like to sincerely thank all of you for joining this webinar. We are thrilled by the level of engagement that we had today, and hope you found it valuable and insightful. So we truly look forward to working with you on some of your projects. So please feel free to reach out anytime. We would be delighted to hear from you. So thank you once again, and arrivederci.